I think we can start. So good morning, everyone. It's still morning. I figured in English speak. I'm Zoltán Lehowski, and this talk will be about turning software into hardware, about the Hastlayer project of ours. So I hope everyone is in the right room. Now, I'm from a company called Lombiq, Lombiq Technologies. We are based in Budapest, Hungary. So probably a few of you have already visited our hometown. There's quite a few British people go to Budapest as tourists. We mainly do software development services. So clients come to us and we develop some software to them, software for them based on the technologies ASP.NET and ASP.NET MVC, and more specifically, we tend to do work with a CMS called Orchard, which is an open source CMS. And we are also a very open source company. We also contribute to a lot of open source projects, but mostly Orchard. And we also have quite some open source repos on GitHub, if you would like to check it out. By the way, I'm one of the co-founders of Lombiq. It's a 3-year-old company, and the other co-founder is Benedek there. So, hi Benedek.
Hi.
Now, although we mostly work with clients, and our clients are from all over the world, exclusively foreign, not from Hungary, mostly from North America and Western Europe, including UK, including the National Institute for Health and Care Excellence, as it is called today. But we also have some research and development projects of our own, and Hastlayer is one of them. These R&D projects are those projects that we do with our own resources, from our own ideas, with our own business model, if there is anything. And sometimes, and most of the time, they are also open source, or eventually will become open source like Hastlayer. So what's Hastlayer about? It's about turning software into hardware, as the talk's title already has given it. But let's specify it a bit more. We are actually talking about taking some logic that was expressed as software in program code and creating an equivalent logic in hardware code for it. When I'm talking about hardware, I mean logic hardware. So you know from school, AND gates, OR gates, everything that can be built with transistors, multipliers, arithmetic little processors, stuff like that. But let's specify it a bit more. We are actually talking about taking a computer program and turning it into the computer chip, because it's not just any logic hardware freely floating somewhere, but it's really like a computer chip. But not an actually existing manufactured computer chip, but an Fpga chip, because we are using FPGAs. Now, what's an FPGA? The acronym stands for Field Programmable Logic Array. So it also deals with logic circuits. Basically, FPGAs are computer chips that, within certain limits, can behave like any other logic circuit, any other computer chip. So if you want to build a computer chip that adds two very big numbers or multiplies two very big numbers, you can configure an FPGA to behave like that. If you want to build a processor, you can configure an FPGA to behave like that. Of course, again, there are limitations, so I couldn't take an i7 CPU and configure an FPGA, but smaller and slower logics can be put on an FPGA. So we are using Hastlayer to produce FPGA implemented logic from software. I also have some Fpga boards here. So they have the advantage that you can plug them into your computer in various ways. I will also talk about them a bit later. And you can, without switching anything, without manufacturing anything, produce logic hardware. So let's get back to the definition again. So what actually we are doing, that we are taking a computer program and turning it into FPGA logic. What's more, we are not talking about just any computer program. So we have a subset. We are actually processing .NET software. Now, who is a .NET developer here, by the way? Oh, quite a few. I thought there were just one. Well, then you know, the others probably not, that .NET is a programming framework, but it's also a virtual machine-based execution environment. And this requires that all .NET programs be compiled to a common assembly type language called Common Intermediate Language. So if you write a .NET program, you can write it in C#, but also functional languages like F#, but even scripting languages like PHP, JavaScript, Ruby, Python. All of these languages, in the end, will be compiled into Common Intermediate Language, CIL, assemblies. And Hastlayer processes that. So this has the advantage that you can work with Hastlayer from any .NET languages. And we turn that into FPGA logic still. One final note on the implementation details. We are actually not directly creating FPGA logic, but we are creating code, we are generating code in a language called the VHDL. VHDL stands for Very High Speed Integrated Circuit Hardware Definition Language. I hope everybody got that because I ain't gonna do it again. Anyway, it's a hardware description language, so it's code that you write hardware in, not software, but hardware. It kind of looks like a software language, a programming language, but it really isn't. In the end, that code will be used to generate, again, logic circuits. So what we do is that we process the CIL assemblies, try to get the logic out of it, then create equivalent logic in VHDL, and then we use the FPGA manufacturer's own software to generate the FPGA specific logic from it. Now, I said that VHDL is code, so we as software developers, because at the keynote speak, basically everybody raised their hands that they are programmers, so I'm in good company. We as software developers would think that, okay, we are writing code in VHDL, so it's kind of like programming, right? Well, it certainly isn't like programming. It can look like programming, but it really isn't. It requires a completely different mindset. It's a completely different paradigm. If you have a for loop in software, well, that will be a sequential execution. If you have a for loop in VHDL, that will be that many components generated in hardware. That was just one example, but you have to really switch mindsets between the two. I'm just saying this because it's quite hard to create a software that takes logic out of a program and generates equivalent logic in VHDL. We are one of the very few companies who do that. The others are mostly the FPGA manufacturers themselves, because they are creating software called high-level synthesis tools. These high-level synthesis tools are for hardware engineers to write still hardware code, but in C++ and subsets of it. But with Hastlayer, we really aim software developers. So you as a software developer should unlock the power of FPGAs without learning about hardware development. Because why are we doing this? What's the power of FPGAs? Well, we can make software a lot faster. So FPGAs we can use as accelerators for our software, kind of like GPUs. And actually we can make software up to multiple orders of magnitude faster. Of course, I'm not talking about any software, and just parts selected CPU intensive algorithms of software that we can shell out and put on an FPGA, not just everything. You wouldn't put a graphical user interface on an FPGA, but CPU-intensive programs you would, because it can be a lot faster. And not just faster, but it can consume orders of magnitude less power. So a CPU can consume 100, 200 watts of power, a GPU even more. Now, these FPGAs here consume at most 2 watts. 2, not 100, 200, 2 watts. Now, that's not too much if we are talking about a small setup like this, but think about a data center with tens of thousands of computers that all should work on some physics simulation or something like that. These 100 watts spared, saved, these really matter. And we also want to make this experience kind of free, so you get these advantages for free. Well, not actually free, but because you have to purchase the FPGAs, you still have to modify your software a bit to code. It should be as easy for you as possible. But a lot of talk now. Let's see Hastlayer in action. And I will show you how to use it on these two Fpga boards that I have here. I'm now opening Visual Studio, which the .NET developers here are, of course, familiar with. But for the others, Visual Studio is the .NET development environment. You don't have to use Visual Studio to write .NET code, but this is what most .NET developers do. Now, we have a prime calculator algorithm here, a very simple sample. The algorithm is about calculating whether a number is a prime. Now, of course, this is elementary school math, and maybe some of you will say that there are more efficient ways than this, but this is just an example. What the algorithm will do is that it will take the half of the number and loop until that number to try to find divisors of the original number that we want to determine whether it's a prime or not. If it finds a divisor, then the number is not a prime. If it can't find a divisor, then the number is a prime. So super simple. And we are not using a square root here, but rather we are looking to the half of the number because we would need to write our own square root function here, and we didn't want to do that for this demo. Because actually the math.square root function in .NET is not a managed function. It's a native function, a native operation that goes to the underlying system. So we have this isPrimeNumber internal method that contains the actual logic, and we have two interface methods, this isPrimeNumber and rPrimeNumbers, which are the two interface methods. And by interface methods, I mean these are the methods that can be called from the outside. These are the methods that you will actually access when using a Hastlayer accelerated algorithm. You will notice that now here we have some Hastlayer compatible, Hastlayer specific code. By the way, this small sample project is on GitHub now. So on the last slide, I will show you the URL to access it if you'd like to look at it. The simple memory object is contains a simple memory model. Because what's the issue? On an FPGA, if we have the logic wired in, we can't add dynamism to it easily because it's hardware. It's there. You can't just say new object and expect something good to happen. So we need to do something with memory and managing new objects. We use the simple memory logic here, which is basically an array of bytes that you can access in some simplified manner, and that will actually be mapped to some DDR memory on the board. So we have 110 megabytes of memory on this board that you can access from your algorithm. And also you need to use this memory space to pass arguments to the logic that you are writing and pass the results back. So for example, what we do in isPrimeNumber is that first we read out an unsigned integer from the memory, which will come actually from the zeros index, because we just need one memory cell here. It's just 32 bits of space that we need. So we will read out that number that we want to process. We pass it to the already seen isPrimeNumber internal method, and once it's done and we get whether the number is a prime or not, we will write it back to the memory. And everything else will be handled by the framework. So the framework will do the rest. It will take the arguments passed to this method, send it to the FPGA, write it into the memory so this logic can see it, and also it will take the result back and send back to the host PC. We also have another interface method here called rPrimeNumbers. This is doing the same but for multiple numbers. So we pass in an argument here as well by using the simple memory object. This will be the count of numbers, how many are there, and the logic will loop until we reach this number and read out the inputs one by one. Again, calculate whether the number is a prime with this isPrimeNumber internal and write the results back. So basically the same thing, but now n times. Okay, so let's see how it actually works. what we have here is a small console application that utilizes Hastlayer and actually runs the algorithm. This is a console application here, but it can be any application, even a web application, a cloud worker, service, whatever. I have some regions here that I will open up as we proceed with the demo, like Open Sesame. So let's take a look at the first part. Well, first we create a Hastlayer shell, just a method call, and then we configure Hastlayer. Hastlayer also has some events. Here we use an event executed on hardware that will be fired when the method execution finishes on the FPGA. We use this here just to write a console message, a message to the console about the execution. Then we also configure Hastlayer. First of all, we pass the current assembly to it. So if you want to Hastlayer to process and program, you pass the program's assembly to it. We now pass the assembly of this current little sample project. That means that, hey Hastlayer, here's this assembly, process it, turn it into hardware for me. But we will restrict what is processed on this line. We will actually tell Hastlayer to only process the prime calculator algorithm. And nothing else will be touched. For example, we don't need this console application to be transformed. Alright, and the last plumbing that we need to do before actually doing something useful is that we create a new prime calculator object from the class that we have created, and we let Hastlayer wrap it into a proxy. Basically what will happen is that we create an object, a normal object, pass it to Hastlayer, and now Hastlayer will wrap it in a way that it will intercept every method call that goes to that object. And it intercepts them, it hijacks them, and actually transforms them to hardware execution. So we will still call methods on this object, it will look like standard C#, and it will behave like standard C#, but in the background, the communication with the FPGA will happen. So let's see the first examples. And I will also start the program now. Now the small console application starts, and some initialization happens in the background. There will be some network negotiation going on with the FPGAs, and we reach the end of our first samples. You see, first we want to determine whether 15 is a prime. I hope it's not a big surprise for anyone that 15 is actually not a prime, so it returns false. We also have 13, we also pass 13, which probably is a prime, and we also make use of our prime numbers to pass in some unsigned integers multiple times. Here, just 1 will be prime, it will be actually the third number that will be a prime here, 2341, and in the next example, just 13 will be prime. So that's it. You see, these were method calls. They work like method calls. But these were just small samples, not very useful. Why would I use Hastlayer for that? Let's get a bit more hardcore. We will now generate 4,000 numbers. That's a bit more than 4. And all these numbers will be on the upper limit of the unsigned integer range. So quite big numbers, around 4 billion. And we will pass these 4,000 numbers to Hastlayer. But first, let's take a test and use the vanilla prime calculator object and see what happens if I don't use Hastlayer. We will try to calculate the first 20 numbers of these 2,000 numbers on the CPU of this machine. Now this machine is a small laptop with an i5 CPU and a mobile version of it. Let's take how long did it take. On this machine, these 20 numbers took more than 13 seconds, so quite some time. Of course, this is not a scientific measurement. The algorithm could be optimized a lot, whatever, but this is a sample for some comparison. So let's see what happens if we do it on Hastlayer. Well, it's already done. We have taken the same 20 numbers here, but now pushed it to Hastlayer, and it was 60 milliseconds. So more than 13 seconds versus 60 milliseconds. That's a lot faster. But there's more. Let's try this for all 4,000 numbers, and this time it was about 350 milliseconds. This is still a bit too much, because most of this time is taken actually on the communication round trip. These FPGAs that I have here are connected via Ethernet to this computer, which is, well, not a too slow connection, but nevertheless it has some latency, and it's not a slow version. Because these FPGAs are currently clocked at 100 MHz. So not 2, 3, 4 GHz like a CPU, these are just running on 100 MHz. But still, just 350 milliseconds for 4,000 big numbers. Now, let's see something more. What we will do now is that we'll let Hastlayer calculate the exactly same 4,000 numbers, but 10 times. So we will say Hastlayer that hello, take these 4,000 numbers and calculate them for us 10 times. Well, it takes about 4.5 seconds, which is roughly 10 times the 350 milliseconds plus some variation. That's what we expected. But let's see now what happens if we do this in parallel, because I have two FPGAs here, so let's see whether we can utilize both of them. I will make the execution continue, and this time we have less than 2 seconds. So it really worked. It's even less than half the time. Probably, by the way, the last execution was a bit slower than usual because some JIT compiling going on still. But nevertheless, we can just add FPGAs to the system and make everything faster, like we would expect, like one CPU core and then multiple CPU cores. And lastly, let's see what Hastlayer actually creates, because I say that it will create VHDL code from the assembly. So let's take a look at this VHDL code and let's see how it looks like. I had an issue here because I forgot to change a pass, but I will now quickly fix this issue. This is the beauty of live demonstrations, that you practice it a lot of times and still something is messed up live. But nevertheless, this time it worked. So let's go to Notepad++ and see what we created. As you can see, it was created just now. So I'm not cheating. This is hardware code. This is code that hardware engineers, FPGA engineers see and write all the day. You see, we created a component, an electric component called HastIP. IP here means intellectual property, because in the FPGA and hardware development community, these electronic components are called IP cores. Just that's it. So we created an IP core for Hastlayer, or by Hastlayer. It has some ports. That means these are the connections to the surrounding environment. Because we have a framework on the FPGA that sits around the generated hardware to make its life easier, there are basically bits going in and out. And there is a lot of code. I don't want you to look at it because you will get shocked. But one thing to note here, well, one other thing to note here, probably, because this will be more interesting, that we have something with this prime number internal here. Now, what actually happens that for each of the methods that Hastlayer processes, there will be a finite state machine generated in hardware. So I'm sure everybody from school knows what a finite state machine is, because we learn about that and then we forget it and then reuse it consciously. Although we use state machines all the time, but not so explicitly. Now here in hardware we use explicit state machines. It doesn't look at software code it doesn't look like the original code at all. It kind of looks like software code because we have if, else, there's a case statement, which is basically like a switch in software. We have variables, but it's very different. But for example, one thing to note here, that we have this modulo operation here, which is the modulo division that we had in software. So we can make some connections. But for example, one difference with hardware is that in software you can write these operations and like there's no tomorrow. You write a division and another division, a modulo, a plus, minus, whatever. Now in hardware you have to take care because not all of these operations are fast. Specifically the modulo, which does a division, a multiplication and a subtraction in the background, is quite expensive. It takes a lot of time. So you have to think about things like waiting for that operation explicitly. So that's why I say that writing hardware code is quite different. It requires a different kind of thinking. But let's now get back to our little presentation, because we have seen this demo from a software developer's perspective now, but let's do something completely different now, or as they say in Monty Python, now for something completely different. And this will be what the hardware engineer does. So we have taken a bit of a small look at VHDL, but let's see what hardware engineers really deal with. Because I figured all of you are software developers here, so probably you'd be interested in learning about how Hastlayer processes the seal assembly, how an abstract syntax tree is built up, or how we generate the VHDL code with a specific library we built. But I won't talk about that. We can chat about it later if you are interested. I will be happy to show. But this is something that you probably never heard of. So it could be probably more interesting and more inspiring. Now, this is the Fpga board that we use here. It's Nexus 4 DDR, and the type is called. The Fpga itself is by a manufacturer called Xilinx. That's the biggest Fpga manufacturer out there. It's a development board, has a lot of peripherals, a lot of bells and whistles that we don't need, but it's readily available. It costs around $350 US. And it's on the lower end of FPGAs, so basically there are only faster and bigger FPGAs out there. It has a few parts that I would like to show you. It has an Ethernet port, that's what we use here. And this is really using Ethernet as a network, not just as a wire. So the FPGA is actually requesting an IP address with DHCP. It's now currently connected directly to the computer I'm using with peer-to-peer, but it could be connected to a router to a network. It also has a USB cable that supplies power to it, and we can also configure the FPGA with it, and we can also communicate with the FPGA with USB. We have also implemented this, so you can choose to either send data via USB or Ethernet. Ethernet is of course faster. And lastly, but most importantly, we have the Fpga in the middle of the board, that small thumb-sized chip that contains all the logic that we are implementing. And there is, I think the memory chip is just below it. But let's see something else now in action. And this time, it will be the Visual Studio of hardware developers. This is a software called Fpga Board. This is the integrated development environment for hardware engineers via Xilinx. So if you are using these Fpga boards as a hardware engineer, you would use this software. It looks pretty crowded, and it is, but it can show us this diagram here. This is a bird's eye view of what we have on the hardware. These are the different components that are configured now on the FPGA. You can see that it looks kind of like a circuit board, although this is just a high-level diagram of it. But let's zoom in a bit. In the middle, we have something called microblade. This is a so-called soft core processor. This is basically a processor, a small and dumb, but still a generic CPU that's in the middle of the FPGA. We don't use this to do too much calculations, but we write some C++ code that runs on it that deals with the communication. The Ethernet USB communication is processed by the C++ program on the micro-based processor. It was just easier this way, and it doesn't add too much overhead. We also have some notable components here. This here is the system clock and a reset port. So remember, we are talking about hardware, so we need to have a clock that's ticking and giving a signal for the logic circuit to run. We have this here, and we also have a reset. Basically, there is also a reset button here, but that's also a reset wire that will just reset the whole FPGA. We also have some other things on the right-hand side. For example, on this here is the DDR. This is the connection to the DDR2 memory. There is also a memory controller, like it's basically either in a CPU or on other systems on the motherboard. Memory controller, all connected together. We also have similar connections to Ethernet and USB. But that's a lot of ceremony for nothing yet, because we didn't see the main component here, which is just with a microblade, and that's the host IP. So this is actually the hardware component that we are generating. You see that we have all the connections here to the left and to the right with the surrounding system. Basically, this IP core, this component connects to the surrounding bus system. By the way, it uses the AXI bus system, which is the same as in ARM processors. This uses the same bus technology that your mobile phone has in its CPU. But let's dig a bit deeper, and I will open up the so-called implemented design. Unfortunately, I couldn't preload this, so we'll need to wait a few seconds, because Vivado can't just have both of these open. But in the meantime, I will start zooming, because I forgot to do that. Sorry about that. So I will be able to zoom in on the implemented design for you. What we will see in a few seconds is the actual utilization of the FPGA chip. So we will see what is configured on the FPGA. Because the FPGA chip is basically a mesh with all kinds of gates in it and configurable connections. So when you program an FPGA, you will set passes in this mesh. This pass finding is what happens in Vivado, but it happens by taking the input of the VHDL code, of course. So here it is. I will also, well, not yet, but we get a sneak peek at it. It's still loading a bit. I will, of course, make it bigger. All the lightweight parts of this is where we have something. The whole rectangle is the chip. It represents the chip. It's actually a physical view, so that's how it looks. And that's how it would look if you be able to see what the utilization is with a microscope or something, but we can actually see it. I presume with an electron microscope. So the lightweight parts are where we have something. So let's zoom in a bit and check what the different parts are. I will click here. Well, this is not clickable, so let's click here. And if I hover a bit, we will get what it is. This, what I clicked, is a clock. Again, we are in hardware, we need clocks. Actually, there are multiple clock generators here, I think. This component I just clicked is one of them. Let's see something else. What's this here? This is others. I don't know what this is. We need a hardware engineer. Let's see this orange thing here. This is also a clock, but we should find something else here. Yes. This here is an I/O block. So we have all the peripherals on this board: Ethernet, USB, buttons, and a display, a small display, whatever. All of this is I/O. One of these cells that we have pinpointed now here is dealing with that. But if we go inside, we will be able to probably see something else, and indeed, something called block memory here. On an FPGA, well, on this FPGA board, there are actually two types of memory. There is DDR2 memory, which is simple RAM. That's in any computer, but this is just DDR2, but anyway. And there is block RAM. Block RAM is something specific to FPGAs. Now, in this mesh that's on the FPGA, there are actually not just logic gates, but as I also mentioned, there are small processors inside as well that do arithmetic calculations, for example, because it's faster that way. And there are block RAM components too. These are small pieces of very smart, very fast RAM scattered all over the chip. It's really small, like 15 kilobytes altogether, but it can be used to speed up the execution and store some temporary values. And FPGA engineers can make use of that. It's partly also utilized by the automatic system, like you can see it here. So that was what an FPGA engineer says. I hope it wasn't too much, but there's not more of it. Instead, let's get back to the presentation for last time. Okay, so this is state of the art, or this is the state of the art, the state of Hastlayer. But what's in the future? Because Hastlayer is not a major product. It still needs to get better, of course. We need to test it, we need to optimize it, and we will have to get rid of this clunky setup that I have here. So what do we want to do? Well, as I said, Lombiq is quite an open source company. We have a very open source culture. We tend to say that we function like an open source community with a company around it. And that's really what we value. So we want to open source Hastlayer. However, it's not that easy. Hastlayer has software components, but it also has hardware components. And open sourcing those is not as easy as pushing to a GitHub repository. Well, first of all, pushing to a repository is not that easy because source controlling these is not just given. Like with any software project, you have to work a lot on it to make it good. And secondly, there are some legal issues that we need to get through. Also, we would like to create a cloud offering of Hastlayer. So currently, you have to plug the FPGA boards into the computer to use Hastlayer. But what if we could take the FPGAs and the Vivado that you also have to install on your computer and whatever, put it in a data center and just let you use it. And that's what we want. So eventually, you could just take this laptop. Next year, on another conference, I would just be able to take this laptop without the rest of the stuff here, connect to a remote data center, and run the code in the same way there, and still get the benefits. Of course, there will be a latency, but nevertheless, it will be a super simple way of accelerating your software in multiple orders of magnitude. And this is not just a dream to have FPGAs in the data center, because it seems that the world is going in that direction. So a few years ago, GPUs weren't in the data center, and now you can use GPUs as a kind of accelerator for your software. In a few years, and that can be just 1-2 years probably, we will have FPGAs as the same commonplace in data centers as well, because Intel is really working on that. They unveiled their new Xeon, one of the new Xeon processors last year, or even 2 years ago, that has an FPGA, well, not integrated in the CPU, but just besides the CPU. Intel last year also bought the second biggest FPGA manufacturer called Ultra, because they definitely want to incorporate FPGA technology into their CPUs. So we think, and we bet on it, that very soon FPGAs will be just another way of accelerating your software, and you as a software developer will have another tool to use. at your disposal. And if you use Hastlayer or similar tools, it will be quite easy to do. So that was it for today. Thank you for your attention. If you are interested in Hastlayer, let's chat after that in the break or later. You can also write me an email. There's also a website for Hastlayer, but there's not much, well, there is actually a lot less information than what you have heard today. We also have a small landing page specifically for ProgSCon under lombiq.com/psc. If you are interested in Lombiq a bit more, or if you'd like to get these slides or get to the sample project on GitHub. So, thank you. And on time. Go.
I have a question regarding cryptography performance of FPGAs. Do you think that's possible, reasonable, and economically feasible to make a Bitcoin farm, mining farm with FPGAs?
That's actually so feasible that they have already done it multiple times.
ASICs?
It's not faster. Yes, a good point about that. By the way, ASIC is, well, I don't know what the acronym is, but basically it's integrated circuit manufacturer. The difference with FPGAs is, of course, that you have to manufacture it, but it can be more efficient than an FPGA and cheaper on the long term, and also faster. It's not faster to use FPGAs than ASICs. Well, of course, it depends on the ASIC and the FPGA, because there are high-end FPGAs, multiple tens of thousands of dollars that are very fast. But it's much easier to use FPGAs, of course. And on a small scale, and I think that a Bitcoin farm is a small scale in this manner, FPGAs are also cheaper. And there are Bitcoin farms with FPGAs. About cryptography in general, yes, that's a good point, because those are those kind of algorithms that are very good to accelerate with FPGAs as well. I'm not entirely sure whether Hastlayer has its place there, because cryptographic algorithms are not something that you write yourself. There are just a few sets that are used everywhere. So probably fixed accelerators are better for that if you really need it, but most of the time you don't need it. So for example, for SSL, it's in web services, it's not an issue. It's not an overhead. But we will eventually also experiment with cryptographic algorithms to see how it works and whether it's feasible.
I mean, doing the SSL is not breaking the SSL, which is not registered.
Oh yeah.
Breaking the SSL might be an interesting game as well.
Yeah, breaking SSL. Breaking cryptographic code is also something interesting. We haven't done it, although breaking, for example, RSA, the algorithm itself is, I think, surprisingly simple. So eventually we will port it to Hastlayer, make it Hastlayer compatible, and also see what happens. These are interesting things. We are not there yet to do full-scale testing. As I mentioned, the system is not mature yet, but that will be very interesting too.
Thank you very much.
Thank you.